So we said earlier when we started looking at electromagnetic radiation, kind of talking about the two models, the particle model and the wave model, we said that the wave model had a really hard time gaining traction just because the big supporter of the particle model and one of its developers was Sir Isaac Newton. And again, because of his kind of heavyweight status in the physics community, it was really hard to challenge him. But Newton, like all people, has to die. He had to die eventually. And he did, and eventually his influence kind of waned a little bit. And this is where the theories of Huygens and others started to kind of get a little bit of traction. But of course, proposing this whole idea of light as a wave in the, after the years of kind of Newton's corpuscular theory, this was going to take a little bit more than just, hey, light's a wave. They have to be able to back that up. If you're going to make a claim, you better have evidence to support that. So the big piece of evidence that came for the wave model of light was from this experiment done in 1801 by Thomas Young. So he performed his famous, what we call the double-slit experiment, and this gave solid evidence for light behaving as a wave. So basically what Young had done is he had kind of taken sunlight, and what he had done is he had just gotten a single beam of sunlight. Like, he wanted to ensure that he had a source that was consistently in phase. Like, he didn't want to use two separate sources that were out of phase with one another, just because that would be methodologically problematic. So what happened is he would take this beam of light, and what he did is he used a really thin card to split that into two separate little beams. Now what he noticed on the screen is he noticed this interference pattern, or he noticed this alternating pattern of bright and dark spots. So this comes from interference that we talked about in Physics 20. So like these bright spots are areas of constructive interference. These dark spots, these are areas of destructive interference. And this could only be explained by treating light as a wave and actually extending back to Huygens Principle. Because if I kind of look at my barrier here, we have this wavelet, we can see these concentric circles moving out, and for certain we can have like an interference pattern formed by these concentric circles. We'd be doing the same idea with Young's double-slit experiment. We just have a slit here and a slit here. So what we're really looking at is we're looking at diffraction. And using Huygens Principle, we could explain these results theoretically, and then of course we have the experimental evidence for those theoretical results. We actually have an interference pattern. And as I mentioned, the only way we can actually get that interference pattern is to treat light as a wave. If we treated light as a particle, basically what light as a particle would say is, okay, where the beams kind of overlap, we should have like a really bright spot, and then it should fade away on the sides. This is not what we're seeing. We're seeing that alternating pattern of bright and dark. So this gave good evidence for the wave model of light. Now, before we get into the mathematics of this, because that's going to be the big part of this unit, we just want to kind of look at what's going on, and just to kind of set up for our treatment of the mathematical part of this experiment. So again, on this distant screen, you'll notice we have these fringes. Usually when we do the labeling, we're going to label the bright fringes. We don't do a lot of focus on the dark fringes. We'll talk about them a bit, but our focus is usually going to be on the bright fringes. So you're going to see this one in the center here. It's basically like if we have our two slits here, kind of in the center of those two slits, if we look at the perpendicular bisector, or right in the middle of those, we're going to have this bright spot in the center. This is a special one. This is what we call the central maximum. So this is important. A lot of our measurements that we take on the interference pattern are going to be based relative to the central maximum. So that's really important. And then each bright fringe on the side of on either side of the central maximum, we can kind of label them going out as 1, 2, 3, 4. You'll see here negative 1, 2, 3, 4. If you call it positive 1, 2, 3, 4, not a big deal. Like these are the first order fringes, second order, third order, fourth order. So you don't have to say it's like the negative fourth fringe. Like you can say it's the fourth order fringe. So these bright spots, sometimes these are referred to as antinodal lines. And then these dark spots, sometimes these are referred to as nodal lines. It's like where we have those nodes, that's where we talked a lot about destructive interference in Physics 20, whereas when we had the antinodes, we were talking about regions of constructive interference. Because again, the bright spot's constructive interference, the dark spot's destructive interference. So we kind of just want to look very quickly at the pattern here. You'll notice I have some numbers in here. The numbers are not actually important. They're just kind of there to explain some things. I'll explain what's actually important in all this. So what we're going to look at in the interference pattern is we're just going to focus on the central maximum. the first node, so the first dark spot, doesn't matter what side of the central maximum we're looking at. And we're also going to look at the first antinode or the first bright fringe. So either one on either side of the central maximum. So the central antinode or the central maximum, it's located directly between the two slits. And what we're talking about here is, well, if we have a wave that's traveling from the slit to this central maximum from either of these slits, the path length is going to be the same. So for example, in this diagram, it's showing, well, this path length to go from here to here is 3 wavelengths. So this path length here is also going to be 3 wavelengths. If we look in that difference in the path, so we kind of subtract the two, well, they're exactly the same. So we have a 0 wavelength path difference. We talked about in Physics 20, if we want to have constructive interference, we need an integer multiple of the wavelength in terms of path difference in order to have constructive interference, or we have to have no difference at all. So where it's placed here with these paths being the same and having no difference in path, we can guarantee that the central maximum is going to be constructive interference. Now for the first dark spot or the first nodal point, from the first slit here, we're just going to say, okay, the path length's about 3.75 wavelengths. And from this second slit to get to that point, it's about 3.25 wavelengths. Again, the wavelengths values here aren't necessarily important. It's that difference between them. What we're going to notice is at that first fringe, the difference in the path going from the first slit to this point to the second slit to this point, that's going to be about a half of a wavelength. And we said in Physics 20, if you want to have destructive interference, your path length difference has to be some half integer multiple of the wavelength. So a half a wavelength, 3 halves a wavelength, 5 halves a wavelength, so on and so forth. So because at this point where the difference in path between the waves coming from the two different slits is a half of a wavelength, we can guarantee that this is destructive interference at this point. And then lastly, when we get to the first node or first antinode across from the central maximum, so we could say that from this first slit, the path length's about 4.50 wavelengths. This second path, it's about 3.50 wavelengths. Again, these two values aren't really important. It's that difference between the path lengths. So the difference in these path lengths is about 1 wavelength, or is 1 wavelength, and that's the important piece here, is that difference in path length being an integer multiple of the wavelength. This is going to give us constructive interference. Now you could repeat kind of this whole analysis for the rest of the fringes. I'm not going to do that. It's going to follow the same suit, because then the next fringe, or the next dark fringe, or the second dark fringe, is going to have a path difference of 3 halves a wavelength. Then the next constructive fringe is going to have a path length of 2 wavelengths. But basically we're just showing you how we kind of use that idea of constructive and destructive interference and path lengths to get our fringe pattern and kind of look at the mathematics behind it. So just before I finish this out, again, you'll just kind of see here, this is Huygens Principle in action. We have our wave front approaching the barrier, or the two slits. And then from each of these slits, we have these wavelets propagating out in concentric circles. And then what we're seeing is that interference pattern of these concentric circles, or these wavelets consistent with Huygens Principle.